Good morning. I would like to present to you my HRV system, which consists, in addition to the recuperator itself, of a glycol heat exchanger and ducted air conditioning based on a condenser unit and a freon heating/cooling coil. I also have an additional carbon and dust sensor connected to the Kompit controller, which is located in the living room. This is that sensor.
This sensor measures the concentration of airborne pollen and carbon dioxide. Here the controller has an additional menu displaying the current concentration and carbon dioxide levels. Based on this, the controller adjusts the recuperator's fan speed to eliminate additional air pollutants. A relay is connected to the system, which precisely measures the electrical power consumption of the compressor unit. Based on this data, it transmits voltage to both the recirculation fan and to the actuator, which then redirects the stream of less utilized air back to the freon cooling coil and subsequently onward into the house.
The next relay is the GWC relay. It is responsible for switching individual GWC loops depending on a predefined time. In my specific case, this is set to 2 hours.
The main components of the system are installed in the unconditioned attic. I am referring here to the heat recovery unit, cooling coil, refrigerant heater with a recirculation fan, and the glycol coil for the ground heat exchanger system. Starting from the beginnings, and outside the building, on the northwest side of the building, there's an air intake. Here in the video, it's on the left side, and the exhaust is on the right side.
On the underside, to be exact.
The white unit you see down below is the air conditioning unit. Both the intake and exhaust units have an integrated stainless steel mesh to prevent impurities from entering the system. I've heard it's a mistake as it clogs the mesh and restricts fresh air flow into the house, and all contaminants should be filtered by the recuperator. In my case, however, I think it's a very good idea. Between the air intake and the recuperator, there's a glycol heat exchanger for the GWC system and about 12 meters of heavily insulated Spiro 200 pipe. While access to these components is certainly possible, it is considerably easier to simply clean the air intake than the ductwork and the dense fins of the glycol heat exchanger. The unit is located on a stainless steel stand with a drip tray. Its power is approximately 5 kilowatts, serving both to cool the building during the summer and to provide heating in the winter. Last winter season, the unit was utilized for supplementary heating of the building during periods of low temperatures. At that time, there was no drip tray installed, and there was no problem with condensate freezing during the frost because water freely flowed onto the concrete. However, now after installing the tray, I will have to monitor the situation because condensate might freeze on the tray, and it will probably end up with the use of a heating cable. The last elements of the system located outside are 2 loops from the glycol ground coupled heat exchanger. They each have a length of 200 meters. The material used for these loops is a PE water pipe, 40 millimeters in diameter, with a wall thickness of 3 millimeters. They are located here on the side of the building. Both loops on the approach to the building and where they enter the facade insulation layer are insulated to minimize heat or cold losses in the upper soil layers. The pipes are buried in trenches about 2.5 meters deep and approximately 15 meters long, with a width allowing them to be freely laid, as shown in the pictures. Before the GWC exchanger, there is a switching module consisting of an actuator that is positioned at this moment.
A temperature sensor, a circulation pump, and 2 valves that allow for filling and draining the system.
The relay I mentioned earlier handles the individual loop switching. It's placed here. We transition from PE water pipes to brass. For the supply and reduction, I used welded PP pipe. Because of its tightness and no glycol leakage, which has highly penetrating properties. Furthermore, there is no electrochemical corrosion, which would happen if galvanized components were used. The entire system is very well insulated because initially when the pipes weren't insulated, there was a lot of condensation. When discussing this part of the system, it's worth noting the information available online regarding ground temperatures at such a depth. It's often said that the temperature at such a depth is constant, ranging from 8 to 10 degrees Celsius. I believe this is untrue. I assume they might be referring to the average temperature, obligated watchama faucet, popa nakama kafabot, but this is usually not mentioned. According to my observations during the summer in hot weather, the temperature of the glycol coming from the ground, which is effectively the ground temperature, ranges from 16 to 18 degrees Celsius. With the nominal airflow for the building, this allows the air drawn by the recuperator to be cooled to around 21 or 22 degrees, even though its temperature before the exchanger often exceeded 30 degrees. For confirmation, I have some pictures of such moments. The situation is analogous when it comes to the winter period. In my particular case, there was no talk of temperatures around 8 degrees. The ground temperature during the period of the greatest frost, which is usually around 18 to 20 degrees, was only 2 to 3 degrees. This only allows the air to be warm to about 0 degrees, which I believe is very important if you don't have an electric preheater installed. Also attaching photos of this situation. Of course, I'm talking about my specific case here. I think if we were to use Glycol GWC or other systems beneath the building, or perhaps insulated from above with a waterproof styrofoam layer, the situation might improve slightly, but not dramatically. Regarding the entire GWC system, I am generally satisfied. Among the drawbacks, I think the costs would need to be mentioned here. They are not small, and the glycol itself. As for the advantages, I would list its maintenance-free nature, its hygienic qualities, heating the air in winter, and what is less commonly spoken about, which is cooling in the summer. If, say, a premise is to use air conditioning in the summer, was powered by electricity, then these are also savings that must be taken into consideration. As for the operating costs of this system, well, at this moment, it seems to me that the only cost is that of the circulation pump, which in this case runs on the first gear and consumes about 5 watts. The system operates only when there is a clear justification for it, specifically when the temperature is above the set point when it needs to cool the air or when it needs to heat it. During transitional periods, it is switched off. The next part of the system, or rather its heart, is the recuperator. In my case, I'm using a CWK 450/200 Eco unit. The heat recovery unit is oversized and the nominal airflow for the building is achieved when the fans operate at 45% of their capacity. It is equipped with an automatic bypass system, which proves to be extremely useful, especially when working in conjunction with the ground heat exchanger. The air cooled by the glycol solution goes directly into the house and it is not unnecessarily reheated by the exhaust air. The situation is quite similar during the nighttime hours as well. The cool outside air is transported directly into the house. Behind the recuperator is a T-piece with a Belimo actuator for recirculation and the recirculation fan itself. Exhaust air removal is performed in 2 ways, depending on how the entire system operates. In the first case, all the spent air moves to the recuperator and is expelled outside. This is the standard operation of recuperation. In the second scenario, when either heating or cooling is engaged, a portion of the air from the exhaust room, specifically those like wardrobes and communication corridors, is returned to the fresh air intake before the refrigerant heat exchanger, which is situated in this very spot. The reason for this, this procedure is quite simple. When cooling, it's much more effective to cool air at room temperature than air from outside the building. I'm referring to 30 or more degrees during heat waves. The same applies to heating. It's easier to heat air at, say, 19 degrees instead of frosty outside air. In my case, controlling these elements proved to be quite problematic. In the Kompit controller, I couldn't find a function responsible for activating the recirculation fan and switching the actuator based on the air conditioning's operation. The solution turned out to be a relay that was placed inside the electrical box. It monitors the current consumption of the air conditioning unit, and when it's active, it supplies power to both the fan and the actuator. This then causes the recirculation system to engage. Upon the unit's shutdown, the actuator reverts to its initial position and the fan ceases its operation. Positioned behind the elements responsible for recirculation, you will find a freon cooling and heating coil. A qualified team ran the freon line to it from the condensing unit, and I installed the temperature sensor for the AHU kit, as well as right behind it, the temperature sensor for the recuperation system. The subsequent components include plastic distributors, 590 ventilation ducts, and the expansion boxes themselves. All of this is situated within the first 10 cm insulation layer on the ceiling slab. Above these elements are 2 additional layers of polystyrene of the same thickness, along with 2 layers of tongue and groove OSB boards, which are laid overlapping. Part of the connection between the heat recovery unit and the distribution manifolds, both on the supply and exhaust sides, was constructed using flexible ducts to effectively minimize noise. The plenum boxes were also lined with rubber for this specific purpose. I did not use any silencers. Currently, when operating at the first and second speeds, the noise is completely inaudible or almost entirely inaudible.
However, în action at the third speed, both ventilation and recirculation are already perceptible. To conclude, the system works just as it was designed. It delivers fresh air to the building around the clock, simultaneously helping to maintain the desired comfortable temperature. The whole setup works very well with automatic blinds, which seem essential for large south-facing windows, and that's the case for me. If the ventilation system and blinds are set to operate automatically inside the building, the temperature never rises above 22 degrees. You just need to be careful not to unnecessarily open windows during heat waves. As the building itself is very well insulated and equipped with the GWC system, the air conditioning unit operated very little, at a low capacity. In my case, it was worthwhile to dedicate some time to properly adjust the air conditioning's performance so that the recirculation fan speed would no longer generate any noise, and at the same time ensure a sufficient amount of cooling was drawn from the freon coil and heat exchanger, preventing any water condensation within the ducts caused by excessive overcooling. I also consider it extremely important to properly regulate the entire installation, ensuring that each individual room receives the correct amount of air as per the design. A significant challenge for me was placing all the components in the unheated attic. Thanks to this, nothing but the diffusers is visible in the living area. This house, however, necessitated very careful insulation for air tightness. It also proved necessary to construct an igloo, a portion of the respiro pipes located between the glycol exchanger here on the left side
and the heat recovery unit inside the igloo.
It creates a kind of siphon. This is a very critical spot that usually, especially in an uninsulated attic, posing a significant risk of moisture condensation that will have nowhere to drain. As I managed to install all the other vent pipes with proper slopes, I decided on very serious insulation here, as I checked this section several times with a thermal camera and didn't notice any water. The igloo itself also performs its function quite well. It is true that it's also insulated from the ceiling, and I personally think it shouldn't have to be. However, when the air conditioning provides heating in winter, due to minor leaks in the system, the temperature inside the igloo is usually above 10 degrees Celsius. The condensate drain, secured with a dry trap, has been connected to both the heat recovery unit and the glycol and freon chillers. I believe the system is relatively complex. It required quite a lot of work. And however, after analyzing competitors' offers, and I did perform such an analysis, I believe that with the competition, I would have received at most a recuperator with pipes. But with Mr. Porozhevsky, I have a complete system with air conditioning and a GWC. Additionally, I also assumed that the cost of installation by some qualified team would probably double the cost of the entire project.